Okay, so what I'd like to talk about is work from really last spring. So with Ron Donagi and Tony Pantev. So we posted our paper on arXiv a year ago about. So the question is Higgs bundles for, well, let's say non-abelian Hodge viewpoint. On geometric Langlands. So let me just maybe start briefly by pointing out that the geometric Langlands has recently seen apparently a full proof, okay? By Geitscory and a lot of people. And its origins, and we'll be discussing this more today, in a paper of Drinfeld in the 1980s, I guess. Okay, so let me just start with by giving kind of general settings. So general setting, so let's let X be a smooth projective variety. Over the complex numbers, let's say, and U inside X an open subset. Zariski open subset. Okay, then we have a couple of different types of things we can look at. So I'll just say on X first, and then here on U. So we can look at local systems which is representations of pi 1 of X. Or pi 1 of U. Okay. Then by the Riemann-Hilbert correspondence, these correspond to vector bundles with integrable connection. I'll write just VBIC. And on the open subset that let's say D modules on X that are holonomic, regular singular, and that are let's see, vector bundles over U. Maybe the terminology at least would be there. And then by Hitchin, these correspond to Higgs bundles. Which are semi-stable and Chern classes vanish. And then on U, we should also, so let's assume that if X minus U is a divisor with normal crossings, then we can say Higgs bundles that have parabolic and logarithmic and purely imaginary. And this is by Mochizuki. Okay, so Now, as the next comment, so let's just go back to the, so, Hitchin in his paper defined the moduli space of Higgs bundles. And we have a birational map from here to the moduli space of bundles. So the birational map is just forgetting the Higgs field, okay? And so if we can write this in stacky terms, so in stacky terms, it's not exactly the same because this is the moduli space of semi-stable Higgs bundles. This is the coarse moduli space of semi-stable Higgs bundles and semi-stable vector bundles. Whereas here we just look at the stack of all Higgs bundles. So let's write that Higgs. And if you're worried about the definition, this is and then this maps to the stack bun, which is the set of just bundles. Okay, but so for what we'd like to say today, this is maybe a more relevant viewpoint. I'll just be working up to birational transformation mostly anyway. So, and the stack is going to be birational to this, namely, at least for curves, the open subset of stable bundles is also an open subset, which is up to a gerb question, an open subset of the stack. Okay, so, but what's the point? The point is that Higgs is actually equal to the cotangent bundle of Bun. Okay? And now, of course, so this is really true on the stack level, and that's going to generate the same thing on the moduli space level, but only birationally, okay? But so let's explain this. So if we have, if E is a bundle, then the tangent space of Bun at the point E is just H1 of endomorphisms of E. Okay? And so the cotangent space is by Serre duality. By Serre duality, that's the dual of this space, so that's just going to be H0 of endomorphisms of E tensor omega. Well, suppose we're on a curve here. I should probably say, let's say at this point x equals c is a curve. Okay. So, right, this formula, Serre duality just gives you exactly the isomorphism between Higgs and the cotangent bundle of Bun. Okay, so let's see now, where are we? Okay, so this is the setting. Now, the thing, kind of fun thing to look at here is that in the Duke math, in the Manin volume of Duke Math Journal of 1987, this is Ron Donagi, who pointed this out when we were discussing this. In the Manin volume of Duke Math Journal 1987, there are two things happening. I mean, there's other things happening too, but two things which will be interesting for us. One is, what was my order here? Right. One is Hitchin's paper. It's not his self-duality paper, it's his Duke paper. Hitchin says that we have the MH, the Higgs bundle moduli space, maps to an affine space. let's call this F. This is the famous Hitchin map, Hitchin fibration. The fibers are generically abelian varieties. Typically some kind of prim. So I'm being a little vague here about a couple of various details. So to define this, you might want to fix the determinant line bundle of the Higgs bundle. If you fix the determinant line bundle, then the fibers are going to be the prims of bundles on the spectral curve, which have a given line bundle as a trace down to the curve. If you don't fix the determinant, then it's not the prim, it's just a full Jacobian. Okay, but just as a matter of notation, we'll just call this a quote prim, okay? That could be a Jacobian. Okay, right, and then, but then the point is that if we have this rational map from MH down to Bun, then we'll have a fiber which is a prim. Which will be some F inverse of a point. And this map, which again is just rational, this is degree, this is finite map. I mean, it's generic, and you know, I mean, it's not really well defined, but where it's defined, it's a finite map. No, sorry. This is for the case of rank 2 Higgs bundles. In the case of rank 2 Higgs bundles, this is a finite map, and the degree of the fiber, I mean, in general, it's a finite map, but the degree of the fiber is calculated as 2 to the 3g minus 3. Okay. Now, Le Monde, the other thing is Le Monde. So this is a paper about Grinfeld's proof of geometric Langlands. Let's say exploring and enhancing maybe Grinfeld's. Of the geometric Langlands in rank 2. In which, so he says this is the general setup. I'll discuss this a little more later. But if capital lambda is a rank 2 local system on the curve, then there is a, well, let's say unique, I'm not completely an expert on this part, but on any of it really, but it's supposed to be unique in some appropriate way, which of course is now explained in the papers of Geitz-Gorient and everybody. Then there's unique Hecke eigensheaf. Let's call this sort of capital E. For lambda, so lambda is the eigenvalue. And so E is a perverse sheaf for a D module on really the whole moduli stack. Okay. And Le Monde calculates the characteristic cycle. And the answer is sort of interesting, which is that it supported the characteristic cycle of E is supported on the nilpotent cone, which is basically F inverse of 0, okay? Referring to the F here, okay? But in that sense, I mean, I don't think they knew, or at least they didn't officially know of the papers when they submitted the two papers for the same volume. I don't think, as far as I know, I don't think Lemon was using this version of the map, but there's a similar version of the map in the Stacky case. Because in any case, you have, I mean, this is a little bit more of a tautological thing, right? The isomorphism between Higgs and T star of Bunn. So you can say the characteristic cycle is a cycle in the moduli stack of T star of Bunn. You can also interpret it as a collection of Higgs bundles. And the nilpotent cone just means the Higgs bundles whose Higgs field is nilpotent, okay? In other words, it's the cotangent vectors such that interpreted here, it's a nilpotent endomorphism, okay? So that makes sense without really defining the moduli spaces. Okay, so plus the other thing, so and, well, Lemon actually calculates all the multiplicities, which I think is very complicated, would be very far from claiming to understand that at all. But anyway, the answer, so this, you know, so the characteristic cycle of something, of a holonomic D-module is going to be a Lagrangian subvariety of the cotangent bundle. A Lagrangian subvariety of the cotangent bundle, it's half the dimension. So it means that either there's stuff which fiber over the base, it's also conical. So either the stuff that has a positive dimensional fiber, but that's going to be supported on some subvariety of the base, which we'll see in a minute. Or there's the only other possibility to have a conical Lagrangian is the zero section inside the T star bund. Okay. The multiplicity of the zero section which is going to be the rank of the vector bundle, the rank of the generic vector bundle. Right, a holonomic D-module over a variety is going to have a singular locus, and then there's an open set on which it's least or smooth or O-coherent or a vector bundle. And on that open set, it's a vector bundle, and there's some rank, okay? It's just a vector bundle with integrable connection on that open set. Guess what number it is? 2 to the 3g minus 3. Okay. This is pretty fantastic. When Ron told me that was the first, just a couple of years ago, that was the first time I'd heard about that. Okay, so, but there's clearly something happening here, right? Okay. As far as I know, it actually. Quadrics, why is it to the 3g minus 3? Yeah, maybe. What's the intersection number of the vertical cycle, right? The inverse image of a point here with the prim here. But I guess really the way to think of that is that you take a general point here, you look at the vector space. I'd like to know what's the degree of the map from that vector space to the, yeah. In the rank 2 case. In the higher rank case, there's 2 to the something, 3 to the something, and so on. Okay, so, okay. But as far as I know, I'm not a big expert on the history, but people don't seem to to have like noticed this right away. Well, I mean, we'll see here. I'll give you the full, at least conjectural explanation of this. Okay, so, but let me just write down a teeny bit the history of, as far as I know, but again, this is just as far as I know. Okay, so apparently there was a letter by Thomas Hausel, but which was not published or circulated as far as I know. Actually, when we told this to Tomasz, he said, "Oh yeah, I wrote a letter to Hitchin about that a long time ago." As far as I never heard of this before, but maybe it was circulated to some people. Okay, then have to say this kind of vague kind of idea did actually cross my mind while listening to a talk by Faltings in 2005, but I don't think Faltings claims to say that, but he said something or other which kind of vaguely suggested that something like this might happen. Anyway, but then there's electromagnetic duality. I'm kind of leaving you guys to imagine what the thing is that we're supposed to be noticing there, but we'll see that in a minute, okay? But then there's electromagnetic duality of Kapustin and Witten. Which is, closely related in any case to SYZ mirror symmetry. For the Hitchin vibration. And this is part of the next remark in some way, which is Donagi Pantev. Which was started with something about the classical limit. Okay, so classical limit of the non-abelian Hodge correspondence. Then they kind of enlisted me in their program, basically. But they had their paper in their book in Aix-marseille, the first. Not sure what the number is. Like 2020 or 2021, something like that. Okay. But okay, so now let me just say that what's the basic slogan, okay? Basic slogan. The basic slogan is that the spectral variety, so let's say E is the local system on U, which is the open set, some open set inside button. Okay, so it corresponds by Mochizuki's theory to a parabolic, logarithmic, purely imaginary Higgs bundle on, well, put it this way. A Higgs bundle on a bundle with parabolic structure on Bunn that has parabolic structure on the complementary divisor of the open set. Okay. And so what's the basic slogan? It's that the spectral variety let's call this E. Phi. Basic slogan is that the spectral variety of E phi is one of these fibers prim. Inside MH, which is birational to T star of Bunn. Okay. So, I'll explain this in a minute, but a Higgs bundle is going to have a spectral variety inside the cotangent bundle of the thing over which it's a Higgs bundle. Maybe I should really say really log D. If D is the complementary divisor, okay. Because the Higgs field has logarithmic poles along D, so it's going to be sort of in the logarithmic cotangent bundle. Okay, so that's the slogan. Okay. So you see that this slogan just gives them some sort of extra structure to the observation that we had above, because this maps to Bunn, and the degree is equal to the rank of E. The generic rank, the rank over U of E. Okay. So the observation of Hitchin that the prim mapping to Bunn has degree 2 to the 3g minus 3 corresponds with the fact that the local system has rank 2 to the 3g minus 3. Okay. So you might say that this, I would call this the Donagi-Pantev conjecture. Okay. So the Donagi-Pantev conjecture is that not only are those numbers the same, and in fact they're the same for the following reason, that the Higgs bundle has as spectral variety this prim thing, which therefore has degree over the base, which is the rank. Okay. And the rank is the multiplicity of the zero section inside the characteristic variety. Okay, so that's the slogan. Now I just have to explain a bunch of stuff here. Okay. So let's explain the following things. Maybe let me write them over here. Spectral variety. And along the way, let's also talk about the Dolbeault higher direct image. Calculation. What does it mean to be a Hecke eigensheave? I don't think we're going to really use that today, but just for completeness. What is this electromagnetic duality? And what is the divisor D? It's something which, this is a good terminology. Rana and Tony said, okay, because Lemont's terminology was very stable for the bundles inside U, the open set U. So Ron and Tony said if it's not very stable, it's wobbly. So now this is known as the wobbly divisor. Okay, so let me just do those.
The very stable form the theoretically open subset.
Yeah. And so part of the good thing here is that you can just define very stable without even defining stability. It defines an open subset of the stack. It means that there exists. It means there doesn't exist a nilpotent Higgs field. Maybe let me just write down here that this is related to the nilpotent cone. What we want to say how this is related to the nilpotent cone. Okay, so let me first just say what's the spectral variety, okay? So in general, we have, so if we have E and then phi, let's call it. So in our case, this x, so this is why I was calling the curve C, because x is going to be Bun in general. But I mean, it could either be Bun or C. But just the general theory of the spectral variety of the Higgs bundle, and say, okay, so for a higher dimensional base, this really means that phi maps from E into E tensor omega 1x, and that wedge phi mapping from E into E tensor omega 2x vanishes. Okay, so that means that at any point, phi gives an action of the tangent space at the point x on the fiber by commuting endomorphism. So we can simultaneously upper triangularize I mean, it's linear in the tangent vector, so it means you choose a right. Means that the map here maps into an abelian subalgebra of this thing. Okay. So I mean, in other words, if this has dimension 10, you have 10 basis vectors, you get 10 commuting matrices. Okay. So that at any point of x, there's going to be r different eigen-1 forms, which are the diagonal elements when you upper triangularize. And then, so the spectral covering, let's call this sigma in general. Let's call these. Of course, there's no order here. It's an unordered set, but. Okay, so the spectral variety is just a set of points together with their eigenvalues, okay? These guys are elements of T star. Yeah, right, an eigenvalue, this is going to be a linear form on the tangent space. Okay, and so then this is maps down to X, and the Beauvillon-Simon-Ramanan construction says that there's a line bundle on sigma. Okay, so let's just assume that generically, let's assume sigma is sufficiently nice, but this still works anyway, even if it's not generically nice. It just means that you have a coherent sheaf on the cotangent bundle. What I'm calling sigma here is going to be its support, okay? But let's suppose that sigma is really, at least roughly speaking, smooth and maps to X with a degree D map. And then let's call this map pi. Okay. So, and we're only assuming generic stuff anyway in everything we're doing. So, at least if sigma doesn't have some bad singularities or non-reduced or something, then we have a line bundle on sigma, and the Higgs bundle X, E on X, is just the pi lower star of the line bundle. And phi comes from alpha tautological, a one form on sigma. I mean, it's better than a one form on sigma. It's a one form. It's a form on sigma which is in the pullback of the cotangent bundle of X. Let me just say this without writing on the board. So in the case where we're going to be talking about certain types of logarithmic Higgs bundle, then you still have the same situation, but this is maybe a subvariety of the logarithmic cotangent bundle of X. But we'll still have a line bundle on sigma. We'll still have E as the push forward of the line bundle. And we also even still have a tautological one form. In that case, it's a one form on sigma, but not necessarily one form on X. I mean, it's the pullback of a logarithmic one form on X, but when you pull back to sigma, the logarithmic part goes away. You got an actual one form on sigma. That's a little more complicated to imagine, but just wanted to say that in case you want to think about it. Okay, so that's the theory of spectral variety. And so in particular, it means that if we start with a local system lambda on C, on our curve C, at the end of the talk, G will be equal to 2, but for now, let's just take any genus. Starting with a local system on C, this corresponds to a spectral cover, C tilde, which is a subspace of T star of C. Okay. Well, let's call this map again pi. It's a subvariety of T star of C, which is finite over C. Okay? It has, let's say, and this, suppose it's rank 2. Everything I'll say today will be for rank 2 things here. And so this is going to be a 2-to-1 covering. Okay, so this 2-to-1 covering is fairly easy to understand, and we'll be assuming that C tilde is smooth. Okay. Okay, so that's this guy. Now, what about where should I go here? Let me just briefly say, because otherwise you'll be wondering what it is, what's the Hecke eigensheaf condition? Which is we have, so let's call this X now, okay? So now X equals bun. What we really do is we really look at, we fix, in the case of bundles of degree 0, so we can go between bundles of degree 0 and bundles of degree 1, back and forth. In the case of bundles of degree 0, we fix OX as the determinant. Then we fix some line bundle like O of some point for degree 1, okay? But let's just sort of, in the general setup, then you can take the disjoint union of those and so on. The general setup is we have X, then we have Hecke, and then we have X, okay? Let's call this PQ. Sorry, X cos C. So Hecke is the set of Hecke modifications of the vector bundle. Okay, a Hecke modification of the vector bundles. You take the vector bundle, then you take a subspace of its fiber over some point. You take the elementary modification, which is to say, take the quotient and then take the map of sheaves from the full vector bundle to that quotient sheaf and take the kernel. That's another sheaf of the same rank, but changes the degree, okay? And in the case of rank 2 bundles, then there's just two possibilities, degree 0 or degree 1. So in the rank 2 case, it's going to be x0, Hecke, and x1 cross C, or vice versa. And it just means you take a one-dimensional subspace. So the fibers of this, well, I guess this one at least. The fibers of this map. So given a point of x1 and C, the fibers of that map are just the possible choices of a one-dimensional subspace of the two-dimensional space. And so that's a P1. Okay. So this is a nice P1 bundle over the base here. Then so Hecke of a bundle, let's call it V, is, sorry. Let's just say, what's the Hecke condition? So why is this Hecke? This comes from the theory in abelian varieties. You see, this whole theory is the kind of the theory of stuff for abelian varieties, like just classical Langlands and number theory. But in the case where instead of spec Z, you replace that by a curve. And in the traditional case, you have Hecke transformations for any prime number P, which is basically any point in spec Z. And that's replaced by Hecke transformations for any point of the curve. And the main deal here is that those all commute with each other, right? The Hecke algebra is a commutative thing. So you can hope to simultaneously diagonalize those things, not just the spectral things. Okay? So what does it mean to simultaneously diagonalize something? But now instead of a function, you take Hecke operating on sheaves by the sheaf function correspondence and so on. Boiled down to our characteristic 0 case, it means that if we take E, we take P upper star of E, then we take R1 typically, but Q lower star of that. But that should be, right, that's, you pull back here and then you sum over the fibers, right? The Hecke, for in the number theory, Hecke means you've got a bunch, you have like a Z mod P cross Z mod P. You look at all the different one-dimensional, rank 1 Z mod P's inside that two-dimensional thing, and you sum over all those guys. You take your function and you sum over them. Instead of summing, we take the R Q lower star. Now, the condition of being a simultaneous eigensheaf for the eigenvalue lambda is that this thing should be E box times lambda on the product. Okay. So, I mean, I would say, and in fact, went through many decades of my own life feeling that this sounded extremely improbable. I don't see why you should be able to get that condition. I mean, it sounds good to say you can simultaneously diagonalize them because they commute, but I don't think that's a proof. Anyway, okay, this really does happen as it turns out. And as I said, so Drinfeld's theorem is that given lambda, there's such an E. Okay. And he even explains how to construct it, roughly speaking. Okay. I guess let me just try this. This works more easily. Okay, so now let me say a word about this electromagnetic duality. Here in the general theory, let's just add an extra little thing here. In general theory, this is going to be one of a group G, and lambda is going to be lambda is going to be a LG local system for the Langlands dual group of the group. So this is where Langlands dual groups show up. So the base of this thing is the bundle moduli space for the G bundles, and the eigensheaf is naturally an LG local system. This is in any rank. Yeah, I mean, this is now proven by Kähler and company in total, I mean, I guess total generality. In the rank 2 case, what it comes down to saying, because in the rank 2 case, the Langlands duality is between PSL2 and SL2. So it basically means, in our case, this will be SL2, so lambda will be an SL2 local system, but the X is PSL2 local systems, which means it can have degree 0 or degree 1. That's what I'm talking about, the X0, the X1. We have a kind of a semi-idea of what happened in the opposite case, which isn't not completely proven. I mean, it's proven by Kähler and company, but our Donagi Pantev program in that case is not completely done. Okay, so now what's electromagnetic duality? Okay. Okay, electromagnetic duality is the following statement, which is that we take the Hitchin moduli space for the group G, and it's basically the following statement, a pair of statements. If you look at the Hitchin moduli space, you compare the Hitchin moduli spaces for the group and for the Langlands dual group, and it says that there's basically SYZ mirror symmetry. Here, okay. I should probably say, in relation to Claire's course and so on, of course, these are hyperkähler spaces. They're non-compact hyperkähler spaces. That was one of the main things in Hitchin's paper. And so the statement here is that there exists a natural isomorphism of Hitchin bases and two is, you might say, even better, right? So we take a point P. We take the prim up here. Under this natural isomorphism, if you take a point, you take the prim, which is at least take a generic point, take the prim, which is the inverse image, and then you take the prim, let's call it, the prim for LG, and then we take the prim here for G, which is FG inverse of the point. The statement is that prim G and prim LG are dual abelian varieties. I like to call these dueling Lagrangian fibrations, right? Anyway. So, now what does this say? So if lambda Lambda is some point here. Let's assume it's generic, so it maps to a generic point here. So we take a point here. So that lambda, let P be the image of that, so lambda is in the fiber over the point P, right? Then this statement number 2 says that that corresponds to a line bundle on the prim G of the point here. Okay. Now we're in a good setup. So the now more precise version of Donagi Pantev says that this L is the spectral line bundle for E. Winding this down here. So let me just say, what did we do? So okay, so there's a basic question here. So how to put a parabolic structure on the bundle E, which is pi lower, let's say, call it P. I guess where you, G. Right, so if we want, remember that when we say we have a spectral variety, that means that, so this is going to be the spectral variety of E comma phi. This prim has a natural tautological one form on it, which gives you the spectral one form. Okay? But we know, from the other part of Langlands' result, for example, that the D module really does have a non-trivial singular support on some other points, which is concentrated over this wobbly divisor. So I didn't have time to draw the picture of what does the wobbly divisor mean in this thing, but so it means that the Higgs bundle that you get is supposed to not just be a smooth Higgs bundle over all of X. It's supposed to be a Higgs bundle that has some logarithmic structure along the wobbly divisor. Okay. Okay, that's a kind of that's a difficult question. I mean, so we can sort of say that the Donagi-Pantev conjecture is somewhat precise in terms of the spectral variety of over a general point for the Higgs bundle that's corresponding to the Hecke eigensheaf. But it doesn't really tell you how to exactly get Hecke eigensheaf. So Ron and Tony were kind of hoping to prove some versions of the Langlands conjecture by putting the parabolic structure on and using that to create the E. Well, now actually, so Geitsgori and company have already created the E for us. So, but I think this is still an interesting question, which is how do you understand the spectral variety corresponding to E? So in that sense, the generic sort of version of, over the open set version of the Donagi-Pantev conjecture is pretty precise. It says, this is the spectral variety. What's not very precise is what happens on the divisor, because it's not really clear at all how to exactly, in general, how to put a good parabolic structure. And so that's what we did. So that's what they did for P1 minus 5 points. And we did this for G equals 2 in rank. And this is rank equals 2. Also. And we also showed, this is with the parabolic structure. We also showed, using Grinfeld's construction, that in rank 2, rank equal 2, but G, any genus, that the predicted spectral variety is correct. But without parabolic structure. Okay, I think that's it.